Learn like a pro.
Hey everyone, and welcome! This is your ultimate exam guide for mastering polymers. We're going to break everything down into super clear, simple steps so you can walk into that test feeling confident and ready to absolutely ace it.
Okay, so let's start with a bit of a riddle. What on earth could possibly link a raincoat, a non-stick pan, and a parachute? I mean, they seem completely unrelated, but trust me, there's one single chemical concept that connects them all.
And the answer is polymers. So what are they? Well, a polymer is basically a giant molecule, a macromolecule that's built by linking together thousands and thousands of small repeating units. And we call those little units monomers. Think of it like this. Monomers are the individual Lego bricks, and the polymer is the huge castle you build with them.
Right then. Now that we know what they are, let's get into how they're actually made. Welcome to part 1, Mastering the Basics. We're going to look at the 2 main recipes for building these incredible molecular chains. So, when it comes to making polymers, you've really got 2 main recipes to remember. First up, on the left, is addition polymerization. This method uses identical monomers that all have a carbon-carbon double bond. Now, the key thing to remember here is that no atoms are lost. They just add together to make one single huge product. Then on the right, we've got condensation. This one's different. It uses 2 different monomers that react, and in the process, a tiny molecule, usually water, gets kicked out.
Let's dive a little deeper into addition. So you start with a whole bunch of identical monomers, and they all have that crucial carbon-carbon double bond. Then, when you crank up the heat and the pressure, those double bonds pop open. This allows all the monomers to link up, hand in hand, forming one long continuous chain. It's like a line of people joining hands. Nobody drops anything. They just all link up. Simple as that.
And here's a perfect visual of that process. This is the making of polyethylene. You can see the ethene monomers on the left, each with its double bond. The reaction opens that bond up, letting them form that long polyethylene chain on the right. And this is the super common plastic used for things like plastic bags and cling film.
You'd be surprised how many everyday things are addition polymers. There's polystyrene, made from styrene, which is hard and light, perfect for takeout containers. You've got PVC from vinyl chloride, which is used for everything from pipes to raincoats. And then there's polytetrafluoroethylene. That's the non-stick, heat-resistant stuff coating your frying pan.
Okay, let's switch gears to our second recipe, condensation. So here, you start with 2 different kinds of monomers. They react at their ends, at their functional groups, and form a bond. But here's the key difference. Every single time a link is formed, a small molecule, usually water, gets kicked out or condensed. Imagine 2 people shaking hands, but with every handshake, they drop a little water bottle. That's the idea.
A classic example of this is nylon. It's formed from 2 different monomers, a dicarboxylic acid and a diamine. When they react, water is removed, and they form this incredibly strong connection called an amide linkage. And the chemical nature of that bond is exactly what gives nylon its amazing strength, making it perfect for things like climbing ropes and parachutes.
Another crucial one you've got to know is terylene, which is a type of polyester. The process is really similar. This time, a dicarboxylic acid reacts with a diol. Again, water is eliminated, and this time it forms an ester linkage. This bond creates fibers that are not only strong, but also resistant to creasing, which is why terylene is so popular in our clothes.
Okay, you have totally got the theory down. So let's move on to part 2, applying the knowledge. This section is all about a core exam skill, how to look at a finished polymer chain and work backwards to figure out what it was made from.
So a really common exam question is working backward. For an addition polymer, it's a simple 3-step trick. First, just scan the chain and find the repeating 2-carbon unit. Second, mentally break it off from the rest of the chain. And third, just put that carbon-carbon double bond right back between those 2 carbons, and boom, that's your monomer.
Let's try it out. Here's a chain of PVC. We find that repeating unit. See it? The 2-carbon piece with the chlorine atom? We break it out, and then we just reform the double bond between the 2 carbons. And there you have it. The monomer is chloroethene. It's a pretty straightforward process once you get the hang of it.
Now, condensation polymers are a little more complex, but honestly, the logic is the same. First, you've got to spot that special linkage, the amide in nylon or the ester in terylene. Second, you mentally break the chain right at that link. You're basically just adding the water molecule back in that got kicked out before. You add an OH group back to the carbon with the double bonded oxygen, and you add a hydrogen back to the nitrogen or the other oxygen.
And this slide shows exactly how to do that for nylon.
You spot the amide link, you break it, and then you add back the H and the OH from water. So the C double bond O side gets the OH, which reforms the dicarboxylic acid, and the NH side gets the H, which reforms the diamine. And just like that, you've found the two original monomers.
Fantastic! We have absolutely nailed the chemistry. Now let's zoom out for part 3, understanding the impact. Because as useful as these materials are, we really have to talk about the problem with plastics.
So why are they such a big problem? Well, ironically, the very thing that makes them so durable, their chemical stability, also means they are non-biodegradable. Bacteria and fungi just can't break them down. This means they just pile up in landfills, taking up space and causing land pollution. And if you try to burn them and don't do it properly, they can release toxic carbon monoxide gas into the air.
So what's the solution? Well, recycling. This table breaks down the two main ways we do it. Physical or mechanical recycling is the simple one. You just melt the plastic down and reshape it. You don't change its chemical structure. Chemical recycling, on the other hand, is much more advanced. It actually uses reactions to break the polymer chains down, either into smaller molecules for fuel, or, even better, all the way back into their original monomers so we can make brand new plastics.
One really important chemical method to know is acid hydrolysis, and it's used for polyesters, like terylene. Basically, it uses an acid catalyst to completely reverse the condensation reaction, breaking those ester links and turning the polymer waste back into the valuable monomers it started from. Pretty cool, right?
But this begs the question, if we have these recycling methods, why is plastic pollution still such a massive issue? Well, the reality is complicated. Economically, it can actually be more expensive to collect, sort, and process plastic waste than to just make new plastic from scratch. Socially, it relies on all of us being aware and willing to sort our waste properly. And environmentally, the recycling plants themselves can create polluted wastewater that has to be treated carefully.
All right, we have covered a ton of ground. It is time to put that new knowledge to the test. Welcome to your final exam review. Okay, first question for you. Take a look at the structure of terylene on the screen. Was this formed by addition or by condensation polymerization? And as a little hint, look closely for that special bond. What's that linkage called?
And for your second question, here is the structure of polyethylene. This is one of the simplest polymers we talked about. Can you tell me the name and draw the chemical structure of the monomer that it's made from? Go on, use that decoding skill we practiced.
You have absolutely nailed it today. We've covered how polymers are made, how to decode their structures, and the huge impact they have on our world. Which really just leaves us with one final big picture question to think about. We've mastered the chemistry of today's plastics, but what will the polymers of tomorrow look like?